Today we were going to cover logistic regression and multiple logistic regression. So in a sense, this is going to be relatively similar to the multiple and linear regressions that we did, but instead of using continuous variables as our dependent variable, we'll be using more dichotomous variables. So if we wanted to predict whether or not someone has diabetes, or if we wanted to predict whether or not someone has high blood pressure, these are instances where you would use logistic regression instead of a linear regression. So why logistic regression? So the previous regression models that were covered focused on quantitative outcome variables, which had an underlying continuum. But there are also important applications of regression in which the outcome is binary. So underlying continuum might be if we wanted to predict days of resistance training, but binary outcomes again might be something such as, we could even just say sick or not sick. Those would be binary outcomes. So again, why a logistic regression? Some dependent variables are dichotomous. Again, things like graduated from college or not. How can we predict who graduated from college or not? Have diabetes or not? Have high blood pressure or not? Logistic regression is then going to allow us to predict these binary dependent variables without violating the assumptions of regression that can lead to nonsense results. What we'll get is a predicted probability of an event happening. So let's take just a basic example of two variables and see if we can talk about if a relationship exists, because this would be a nice way to lead into doing the actual logistic regression. So in this case, we have diabetes and then hypertension. Both of these are dichotomous variables. It's told to have diabetes or told to have hypertension or high blood pressure. And we have yes or no. So this is no, that's yes, 0 is no, and then just yes right there. So let's look at what percentage of people are told that they have diabetes. So in this case, if you wanted to look at this, you need to type in comma column. You could also type in comma row to get the information for high blood pressure. But in this case, we can see that we have 10.78% of people that were surveyed were told that they do have diabetes. So we just look at, it's 152 people were told that out of the 1,410 people. So again, there's the people that are told that they have, in this example right here, is people that are told that they have diabetes, but not told that they have high blood pressure. And then over here is people are told that they have diabetes and also told that they have high blood pressure. Now, if you even just looked at the percentage of people that are told that they have diabetes or told that they have high blood pressure, we can look at the differences right here. So 23% of people who have diabetes were also told that they have high blood pressure. And then people that were told that they didn't have high blood pressure but also had diabetes, that's only 5.8%. So if you just look at this right off the bat, we can say that of the people that have diabetes, we can also see that 23.6% are also told that they have high blood pressure. So let's talk about the odds of having diabetes just by looking at this column. And we can just do this by taking the people that have it divided by the people that don't. So that just gives us the odds that you're going to have it. So in this case, we have 12%, so 0.2. Just looking at that right there. So what about the odds of having diabetes if you have hypertension? And this is just going to be a little bit of a better way to look at the relationship between these variables. So we can say the odds of having diabetes if you have hypertension, so there's our yeses, is going to be 93 divided by 301. And that's just 0.308. But the odds of having diabetes if you do not have hypertension is going to be, is going to be this number 59 divided by 957. And if we look at that, that number is much, much smaller. So we can have a good idea that there's going to be a relationship here between these two variables. So we'll go through an example. Again, we've already seen this tab diabetes. So people that are told that they have diabetes, 153 have been told that they do, 10% of the people. And then over about 1,260 people are told that they did not have diabetes. So why would we run a logistic regression? In this case, I ran a regression just to show you that it wouldn't exactly make sense. Because these variables are dichotomous, had or did not have. Now this look at this number right here. That wouldn't make sense. We can't say what are we going to go if we go up 1 unit in weight, how can we go up any more units in diabetes? Because this is just conceptualized as a 0 or a 1. It's not a continuous variable, so this wouldn't necessarily make sense. So in this case, because we have this binary yes-no variable, we're not going to be able to actually run a regression. So anytime a dependent variable is yes or no, we can't run any kind of regression. We need to move over to a logistic regression. Now, logistic regression only understands zeros and ones. So what you actually have to do is recode your data. In this case, this is what that's going to look like. So I've already actually recoded everything. But when you type in tab diabetes, no label, I'll show you this. I'll actually recode it back to how it was. So tab diabetes, comma, no label. Make sure you're adding that just so you see. So I've already had 0 and 1. So initially that wasn't what the case was. But if I did tab diabetes, we can just see that told have diabetes is 1 and no is a 0. So if we were just going to redo this, when you do tab diabetes, it's going to come up as a 1 or a 2. So in this case, you actually have to recode it. So I'll actually just show you what the original one was so that you know how to recode it. So we're going to recode. That's all you got to type in is recode diabetes. And we're just going to make our 0 equal 2. Just so that we can go back to that. And then we'll change it again. So then I'll just go tab diabetes. And then I'll go no label. And I believe this is what you would see is 1 or 2. So 1 being yes, they were told. 2 being no, they didn't have it. So all you would now do is recode diabetes. And we're just going to do 2 equals 0. And again, this is because logistic regression doesn't understand 1 and 2. It only understands 0 and 1. So we are just going to show you this again. We'll go with tab diabetes, no label, and then we have our 0s and 1s again. Okay. So again, you're just running that code. Recode diabetes 2 equals 0. So now what if we wanted to run a logistic regression? You don't necessarily have to do this when it's just one variable, but it's good practice to put a C dot in front of continuous variables. Weight is a continuous variable. So we ran this regression, so I'll type that in for you. We're just going logistic, and we are going diabetes C dot weight. And that's the output that we're going to get, and that's the output that we'll see right here. So what do we have? 1, is the relationship between weight and having diabetes significant? Yes, it's significant. Now, let's interpret this. So this is also going to be important to look at right here when you're running multiple logistic regression analyses. In this case, weight is significant. So what does this mean? You'll notice this is a different number than what you would see, or a different label than what you would have seen when you're running linear or multiple regression analyses. So all that this means is that for every 1 unit increase in weight, there is we go over 0.97% increase in probability of having diabetes. So each increase in 1 unit of weight increases the odds of having diabetes by 0.9%. That's how we want to write this down. increases the odds of having diabetes by 0.9%. So how do we get that? When the odds ratio is more than 1, the interpretation can be simplified by subtracting 1, then multiplying by 100. So here we have 1.009 right there times 100, we're getting 0.9. So it's really about 0.97. So for every 1 unit increase in weight, we are basically just seeing almost a 1% increase in the odds of having diabetes. And that was already up there. So what if we were going to, so that was with a continuous variable. What if we were going to do this with a dichotomous variable? So like what we showed in the beginning with hypertension and diabetes. What if we wanted to do sex, so someone's gender? So we have males and we have females. And when we do tab sex, no label, we see that we're just looking at 1s and 2s. So we actually want to swap, we can switch that over. So this would be our output. Now with the dichotomous variables, especially if it's just these two, it will tell you what their reference category is. So in this case, men are the reference category. When we look at this though, we can clearly see that it's not significant. So there's really not much to be said here about actually doing a logistic regression as sex is the dependent variable. But I just want you to look at this. You'll see a reference category. Now, if this was significant, notice that this is lower than 1. So if it was significant, we would say that men have about a 10.5% reduction in the odds of having diabetes. But it's not significant, so we don't say that. So let's use hypertension. We've already done this. We have hypertension. We'll recode hypertension to 0 and 1 variables. Although you don't actually necessarily have to do this if this is not the dependent variable. You always want to make the dependent variable a 0 or a 1. So you would have been fine with just keeping this as 1 and 2 as well. But we've already talked about this kind of data. We have hypertension, told they have it, yes or no, and then the frequency as well. So we put an I dot in front of this variable. In this case, we only have 1 reference category, so it's told that people have hypertension. So let me move this down. So we're trying to predict whether or not someone has diabetes based on whether or not they were told they have hypertension. So in this case, we look at the model. Is it significant? Yes, it's significant. Yep, it's significant right there. And we see that our odds ratio is 5.01. Okay, so in this case, we're doing 5.01 minus 1 times 100. So there's a 401% increase in the probability of having diabetes if you're told that you have hypertension. And this makes sense because usually comorbidities operate together. So if you have high hypertension, the odds of you having diabetes is also higher. Now, what if we wanted to do a multiple logistic regression? So in this case, we have diabetes. We have a dichotomous variable, again, symbolized by the I dot. And then we have a continuous variable that we've already talked about, weight. So if we did logistic diabetes, we want to predict whether or not someone has diabetes based on whether or not they have hypertension and also what their weight is as well. So what we see here is that, yes, it's significant. This pseudo R squared is similar to what we had in the multiple regression. I'm not going to ask you too much about this, but for the most part, we're just looking at, is this model significant? Yes, it is. Are both the variables significant? Yes, they are. And so right here what we have is a 0.7% increase in the odds of having diabetes for every 1 unit increase in weight. And then also we have a, so now this would be, what's 4.5 minus 1, so we would have a 350% increase in the odds of having diabetes if you're told that you have hypertension. What if we wanted to throw in another variable? What if we wanted to throw in someone's years of education? In this case, education is a continuous variable, so we put that C dot right in front of it again. And again, look at this. It's significant. Now, are all these variables significant? Yes. So we have this is below 0.05, and these are all much, much lower than 0.05. So what we're seeing again, weight hasn't really actually changed that much. So it's still about a 7% increase in the probability of having diabetes for every 1 unit increase in pounds. Hypertension is pretty much the same, almost unchanged. But now this is one where we actually see an inverse relationship. So there's about a 6.5% reduction in the odds of getting diabetes for every 1 unit increase in education. And this probably logically makes sense. People that are more educated probably make healthier decisions. People that are less educated probably make less healthy decisions. So that one makes sense too. So all three of these variables in our logistic regression are significant. So what if we just, instead of doing the continuous variable, what if we used ordinal variables? So what if we were using ordinal variables? So in this case, we did degree instead of education. So we have respondent's degree, highest degree, we have less than high school. We have high school, junior college, bachelor, or graduate degrees. We wanted to do tab degree, no label, so we can see what all of these represent. So 0 represents less than high school, 1 represents high school, 2 is junior college, 3 is bachelor, 4 is graduate degree. Now, notice here I put IB0 next to my degree because I wanted to make our 0 category our reference category. So now in this case, all of these other variables are being compared to less than a high school degree. Now in this case, there's no significant differences between any of these variables and having diabetes. So the reference category right here, less than high school degree, these people are no less likely to have diabetes. Although this one gets a little bit close, gets slightly close. But I just wanted to show you that you can the way to change a reference category. So if I did this, maybe I want to make a graduate degree my reference category. All I did was go from 0 to 4. And again, nothing's really significant, but we still have weight and hypertension being significant. All right, so that is the end of logistic regression. You'll get some practice questions, but just big things to remember are our dependent variable is always going to be dichotomous. Add these, if you have a ordinal variable with multiple reference categories such as education, make sure you're typing in what you want the reference category to be. Okay. What we look at for the output is odds ratio and also is it significant. So in this case, we're just talking about increased probability. So the way that you should be writing it down would be, so for example, each 1 unit increase in weight increases the odds of having diabetes by 0.9%. If you're looking at reference categories, such as high school, junior college, bachelor degree, stuff like that, we might say the odds, let's just pretend like this was significant, the odds of having diabetes is 45% less for people with a bachelor's degree than those with less than a high school degree. So that's how we would just do those two comparisons.